We're going to take a look at what a series is. So this is going to be just a basic introduction to them. First thing is defining a series, and it is the sum of a sequence. So anytime you have a sequence, it's when we add it together, that's when we get a series. Now, for notation reasons, we are going to be using this capital Greek letter named sigma, and it will be commonly referred to as summation notation or sigma notation. And with capital letter sigma, what that means is to add all the things. So we will be using sigma notation quite often. So let's say we have a problem that looks like this. It says evaluate, and then it gives us this problem here. And we have this sigma, and then we have 2i plus 3. Well, now a couple things that come along with this sigma. I is what's referred to as our index, and it's kind of just indicating what our variable is. It doesn't have to be I. It could actually be any letter. I is probably the most common one used. The 5 here, that's called our lower limit. That's actually going to be our starting point for when we start to evaluate this. The 10 up here on top is called our upper limit, and that tells us when we're going to stop evaluating. So what this tells me is that I need to add up all the terms that I get when I plug 5 in here, 6 in here, 7, 8, 9, and 10. So I'm going to put each one of those in there. So when I put a 5 in there, I'm going to get back a 13. 2 times 5 is 10, plus 3 gives you the 13. Then you're going to plug in a 6. 2 times 6 gives you a 12, and add 3 and you get 15. So you're going to do that for 5, 6, 7, 8, 9, and 10. Now the reason we're starting at 5 is because that's our lower limit. And the reason we're stopping at 10 is because that's our upper limit. So these two numbers tell us where do we start and then where do we end. And then we just plug in the values there for our I. So when I plug the rest of these in, I'm going to get some corresponding numbers. So now that I've got them all filled in, these are the numbers that I need to add up, because the sigma says I need to take all of these and add them together, and that's going to be my final answer. So when we see a notation like this where it says evaluate and then it gives you sigma notation, you should actually come up with just a single answer as long as you have numbers in here. So we're going to go ahead and add all these up, and then that's going to be our final answer. Okay, when you add these all up, you should get 108. So our final answer is 108. The value of this summation notation expression here is 108. So I plugged in each of my I values from 5 to 10, got their output values, and then added them together because the sigma tells me I need to add all that together. So that's just a basic sigma notation problem. Okay, we're also going to have to do the reverse of this, where we have to write the series using sigma notation. Now, if you look back at the problem that we just did, in order for us to evaluate it, we had to have a lower limit, an upper limit, and we had to have our rule. Well, we're going to have to be finding all of those things this time. Usually you want to find the rule first, and then you want to write it in terms of I, or whatever index you pick, and your sigma, and then you want to include your lower limit and your upper limits. So here's an example we have. It says, write the series using sigma notation. Now the reason this is a series is because we are adding the numbers. If this was just a sequence, there would be commas in between here. So the first thing we have to do is we have to think about what rule would get us to the sequence 5, 10, 15, all the way up to 100. And now remember, we start, since it doesn't tell us that we started at someplace other than 1, we are going to assume that n was 1 for the 5 position, and then 2 corresponds to the 10 position, and 3, and so on. So now we can do this a couple of different ways. If you can look at this and see the pattern, so you could ask yourself, what do I have to do to the 1 to get it to a 5? Well, I could add 4. Then come to your next term. Does that pattern still work? Well, 4 plus 2 does not give me a 10, so it's not add 4. I could try something like squaring it and then adding 4. So 1 squared would be 1, and then add 4. Well, if I square 2, I'm going to get 4. 4 plus 4 is 8. So that didn't work. You could try multiplication. So if I took the 1 times 5, that would give me a 5. Then you want to see if it works for the next one. So does 2 times 5 give me what I need? And that's yes. And then 3 times 5 gives me what I need. So our rule, since we've found that it's a times it by 5, our rule would be 5n. So that's the first step here. We found the rule to be 5 times n. We could have found this rule also by plotting the points, and then you would have noticed that it was linear, and then you could have written the equation of the line, and you still would have gotten 5n. Okay, the next thing we need to do is we need to write it in terms of I and sigma. So I'm going to start by making my sigma, and instead of n, I'm going to write it as 5i. And then it says include our lower limit and our upper limit. So down here on the bottom, I'm going to start with I equals 1 because that was the position we started with. But now we have to figure out what position do we end with. And we figure that out by looking at this 100. Now because of this dot, dot, dot here, this ellipsis, we can't just say, well, we end at 4. Because this ellipsis means that there was a bunch of other stuff happening in between here. We have to figure out, well, what position gets us to 100. Well, since our rule is 5 times n, I need to figure out what value of n will get you to 100. Well, divide both sides by 5, and you get n is 20. So this 100 must have been in the 20th position, which means our upper limit has to be 20. So then this would be our series written in sigma notation. We found the rule, wrote it in terms of I and sigma, and then found our upper limit and our lower limit. Okay, we have right now 3 special series. This first one right here represents the sum of n ones. And the reason that is because this is just a constant right here. So let's say n was 5. Well, if I plug 1 into here, this is actually where my formula is here. If I were to plug 1 in here, there's actually no variable to plug it into, so it just stays a 1. If I were to plug 2 in here, it just stays a 1. And plug 3 in there, it stays a 1. Plug 4 in there, it stays a 1. Plug 5 in there, it stays a 1. Well, when I add those together, I just get 5. So it's really the sum of however many 1s we have up here. So it would be equal to n. This next one is a little bit stranger looking. And our sigma notation series is right here, and it's saying if I were to add up all of the positive integers from 1 to n, instead of actually going through there and adding them all up, I could just use this formula. So let's say I needed to add up all the integers from 1 to 3. Now that one wouldn't be so hard because all you would have to do is take 1 plus 2 plus 3 and you would get 6. But when it gets hard is, let's say you had to go up to 2,000 for some reason. Well, instead, we could use this formula, and we'll show you that it works using the 3. I know I should get an answer of 6, so if I plug 3 in here, 3 times 3 plus 1 divided by 2 is 12 over 2, which is indeed 6. So if I have to add up the sum of the positive integers from 1 to n, I can use this formula instead. And then this last one. If I were to need to add up the sum of the squares of the first positive, I could use this formula instead. So that would be like if I needed to add 1 squared to 2 squared to 3 squared and so on and so forth, clear up to n, I could use this formula instead of writing out every single one and adding them by hand. So these are 3 common or special cases that are handy to have, because they can make some problems quite a bit shorter. Hey, here's our last example we're going to do. It says, you are stacking oranges in the shape of a square pyramid that has 10 layers. How many oranges will you need? Well, now when they talk about a square pyramid, that just means our base is square, and then taper up to a point, making the pyramid portion of it. Now, you might want to think of this in terms of layers, in layers from the top. So if I were to do my first layer at the top, so if you think of this pyramid, you would only have one orange if you only had one layer. Now with it being a square pyramid, in order to make a second layer, I would have to put the oranges on like this. But now remember, this is three-dimensional, so you're going to have the oranges in a layer back there. So in our second layer, layer number 2, we actually have 4 oranges. A bird's eye view of this, you would have these 4 oranges here, and then so here would be our top orange. Now if we go to our third layer, this is going to be even harder for me to draw. Our third layer, we would have 3 along this side, and then 3 along that side, and the back, and this other side, but we'd also have to have the middle filled in. So our third layer would actually look like this. And then if we put on that second layer on top of it where it would go, it would be like that. And then our top layer would be right in the middle. So it's getting kind of messy, kind of hard to draw. But if we look at our third layer, we have 9 oranges in that third layer. So over here on our table, layer 3 has 9 oranges. Now, I hope we're going to find a pattern before I have to try to draw the fourth layer, because it's just going to get messier over here. So let's see if we can figure out. When I had 1 layer, I had 1 orange. When I had 2 layers, I had 4 oranges. When I had 3 layers, I had 9 oranges. Hopefully you can recognize that the pattern is we're squaring it. So if I had 4 layers, I would have 16 oranges. If I had 5 layers, I'd have 25 oranges, and so on and so forth. So our pattern is n squared. And the reason for that is because this is a three-dimensional object. So if I have n on this side and n on this side, my area that it would have to cover would be n squared, is why it turns out to be like that. But now if we look back at the question doesn't ask us to find the pattern. The question says how many oranges will be needed. Well, if I think about if I only went to 5 layers, I would have to add all these numbers up. But I'm going clear up to 10 layers. So I could write these all out and then add them all up by hand, and that would be just fine. Or if I go back to our special formulas here, I'm actually trying to find the sum of some squares. So I can use this formula to figure out how many oranges there's going to be. All I need to know is that I need to go to 10 layers. So then I don't actually have to write down each individual number. I can just plug it in here. So I can take 10 times, well, 10 plus 1 is 11, times 2 times 10 is 20, plus 1 is 21. Take that, all divided by 6. When you calculate that out, you end up getting 385. So if we go back to our problem, it would actually take us 385 oranges to make a pyramid that has 10 layers for this one. So that's just an example of how you can sometimes use those special patterns to make your problems a little bit simpler.